When we start taking a rigorous axiomatic approach to geometry, the first thing we need to do is to define what a geometry is, what sort of properties it needs to have. And so for that, we're going to talk about incidence geometry, which is sort of the most basic form of it, dealing with just the points, lines, and planes as sets, and describing what sorts of interactions they must have when you intersect them. Let's start with the definition. So this is definition 4 in the notes. A geometry is a triple SLP where L and P are collections of sets. Collections of sets of points. So the elements of S are going to be called points. The elements of L are going to be called lines, and the elements of P are going to be called planes. Now, we can't just take any random collection of sets that we want. They have to satisfy certain properties. So a geometry has to satisfy the axioms I1 through I5. I here stands for incidence. And we're about to define 5 axioms that tell us how points, lines, and planes interact with one another. Now, I should point out that it's conceivable that you could define something that behaves sort of like a geometry that satisfies slightly different axioms or doesn't satisfy all of these. And you could get some interesting facts out of that. You could prove some interesting theorems about not quite geometries like that. We're going to focus our attention, though, on the ones that satisfy the 5 axioms of incidence geometry. So let's look at what those axioms are. So we've got axiom I1. Given any 2 points, P and Q, there is a unique line containing them. A unique line containing them called, well, we can denote it this way. We can write down the points PQ and write down a double-headed arrow over it. This is to evoke what we're familiar with already in terms of lines. They go on forever in both directions, and so that's what this notation is supposed to evoke. So this is telling us that given any 2 points, there is one and only one line containing them. Now, a point of terminology here. Whenever I specify the number of points that I'm dealing with, this means that the points are distinct from one another. So P does not equal Q here. If I didn't specify the number, if I just said given any points P and Q, that leaves open the possibility that P and Q might actually be the same. And sometimes we want to allow for that. But be aware of that and make sure to use that properly when you're writing down your own proofs. So given any 2 points, P and Q, there's a unique line containing them called PQ, or line PQ. Now, just to make things clear, recall that a line L is a set containing points. So if L is the line containing P and Q, then that means that P is actually an element of L. L is a set, P is an element of that set, and Q is an element of that set as well. Also, note that this description of the line L is not necessarily unique. So for example, if L is the set containing the points P, Q, and R, then L is the line containing P and Q, but it's also the line containing P and R, and it's also the line containing Q and R. We'll actually use this reasonably often in the course of the class, that if you take any 2 points on a line, then you could write down that line as the line containing those 2 points in this notation. All right, so that's our first axiom. Given any 2 points, there is a unique line containing them. Let's look at the second axiom. Axiom I2 says a similar thing, but for planes. Given any 3 non-collinear points, P, Q, and R, there is a unique plane containing them called, well, we can use a similar sort of notation, PQR with the double-headed arrow over it. This notation won't wind up being used quite as much just because of the way we usually construct our proofs, but we can use this notation when it's helpful for us. And just like with a line, there are many different descriptions of a single plane, and as long as you take any 3 non-collinear points in that plane. Now, non-collinear means that they don't all lie on the same line. If a collection of points do all lie on a single line, we say those points are collinear. They lie on the same line. If they don't, then we say the collection of points is non-collinear. So axiom I2 is sort of the plain version of axiom I1. Now we've got axiom I3, which says that if P and Q are 2 points and P and Q belong to L, where L is a line, and P and Q belong to E, where E is a plane, then L is a subset of E. So this is telling us, if we sketch things out a bit, which can often be helpful for us to understand what's going on, to see that what we're talking about here matches with our intuition, what we're familiar with. If we've got 2 points, P and Q, and they lie in a plane, then the line containing them should lie in that plane. What this is saying is that we can't have something like the following, where we've got some line that comes down and intersects a plane at 2 different points, but doesn't actually lie in the plane. So we're saying that this sort of sketch is impossible. Really what axiom I3 is telling us is that our notion of straightness for lines and flatness for planes are compatible with one another. You'll notice that so far when we've talked about lines and planes, we haven't used anything like, well, we haven't used anything like a line as a straight collection of points. that all lie together. And that's because the word straight in the context of geometry isn't defined until we define it. And we define straight actually in terms of lines, not the other way around. So we define lines first, and then we'll describe a straight something or other as being something that lies on a single line. So axioms I2 and I3 are telling us that the notions of straightness for lines and the notion of flatness for planes are compatible with one another. All right, so let's look at axiom I4. Axiom I4 says that if E and F are two planes, then E intersect F is empty or a line. So this is telling us how two planes can interact with each other. So you could either have two planes that are parallel to one another and they just don't intersect at all. That's the case where you've got two planes that are empty, whose intersection is empty. Or you could have two planes intersect with each other, but if they intersect at all, their intersection has to be a whole line. Their intersection can't be just a single point. Really what axiom I4 is doing for us is it's defining that we're working in 3 dimensions. We're only going to be working in 2 and 3 dimensions in this course, but it's perfectly reasonable to do geometry in higher dimensions. And in 4 dimensions, it's actually possible for 2 planes to intersect in just a single point. But axiom I4 is saying, no, that doesn't happen for us. Axiom I4 is specifying that we're working in 3 dimensions rather than anything else. And essentially that comes down to saying that if I take two two-dimensional things that intersect, then their intersection is a one-dimensional thing. Planes are two-dimensional, a line is one-dimensional, and there's some arithmetic there that is related to the dimension of the space that everything is living inside of. So that's what axiom I4 is doing for us. Now, if we look at axioms I1 through I4, they seem pretty complete. They tell us how we can construct lines by just taking any 2 points. They tell us how we can construct planes by taking any 3 non-collinear points. They tell us that the notions of straightness for lines and flatness for planes have to be compatible with one another. And they tell us that we're working in 3-dimensional space. So what's left? There are 5 axioms. Why aren't these good enough? Well, really they aren't good enough because they don't tell us that we don't have really silly geometries. So let's look at an example. Before we go on to axiom I5, let's do an example to see why it's necessary. Let's consider the following geometry, or geometry in quotation marks, because it's going to turn out to not be a geometry once we add in our 5th axiom. S is going to be the set of points A, B, C. L is going to be the set of lines. And this geometry is only going to have a single line, A, B, C. And there are going to be no planes at all. We could sketch out what this geometry looks like. Actually, we could do it this way. A, B, C. So there are only 3 points in our geometry, A, B, and C, and they all lie on the same line. That's what the line going through those 3 points indicates. and there are no planes at all. Well, technically, this satisfies all of the axioms of incidence geometry, though pretty trivially. If I take any 2 points, either AB, AC, or BC, there is exactly one line containing them, namely the only line that exists in the geometry. And if I take any 3 non-collinear points, I get a plane, but there aren't 3 non-collinear points in this geometry. All points are collinear because our whole geometry lies on a single line. There are no planes, so axioms I3 and I4, they are true because you can't find any counterexamples. You can't find any planes that don't satisfy I3 and I4. And so this is a geometry if all we had was axioms I1 through I4. But of course, this is trivial. This is not the sort of geometry that we want to consider. In fact, we can get even sillier with it. We could take a geometry where there are no points, no lines, and no planes. Everything's just the empty set. Technically, this satisfies I1 through I4. Empty space, no points. So clearly this is not what we want. Clearly we need to put in some axioms to say that, okay, yes, we have enough points of certain kinds. So here's where we get axiom I5, which tells us that every line contains at least 2 points All right, so we can't have a line that's just a single point or a line that's empty. Part 2 of this is that every plane contains at least 3 non-collinear points so a plane can't be a line. There exist 3 non-collinear points. So this is the part of axiom I5 which makes our first example fail. Because in our first example up here, there did not exist 3 non-collinear points. So our first example would not satisfy axiom I5. And finally, there exist 4 non-coplanar points. Meaning that our whole geometry doesn't lie in a single plane. Now, for these last 2 parts of it, we could also write there exist at least 3 non-collinear points, and there exist at least 4 non-coplanar points, because of course we can allow for more than those. But axiom I5 just says that we can always find 3 non-collinear points, and we can always find 4 non-coplanar points. So, given this, we've got a couple of non-geometries now because they don't satisfy I5. So let's see, well, what actually is a geometry? Well, let's consider two separate geometries, and they're kind of going to be on the extremes of the scale in terms of simplicity and complexity. So the simplest geometry, that is the one involving the fewest points, is the following. It's going to be a geometry containing 4 points. We know that every geometry has to contain at least 4 points because of axiom I5. Now the set of lines is going to be the following. there's going to be 6 lines, one for every pair of points. So AB, AC, AD, BC, BD, and CD. So that's our collection of lines. And our collection of planes is the set of all triples. ABC, ABD, ACD, and BCD. So we can check the axioms directly from here, but of course this is geometry. We want to understand what's going on sort of visually, and that's usually the better way of doing things, understanding things intuitively. So let's look at this geometry, and I can illustrate it in the following way. I can write down my 4 points, and then I'm going to put a line between 2 points that, or a line segment here between 2 points that lie on the same line. And then let me go ahead and sort of shade in pardon me. Let me shade in the planes. So I've got a red plane here for A, B, and D, I guess. Got a blue plane here for ACD. Got a green plane here for BDC. And then there's a big plane over all of it for A, B, and C. So, looking at this, let's check our axioms. So, axiom I1, given any 2 points, there is exactly 1 line containing them. Well, yeah, that's true, because the lines are precisely the sets of pairs of points. So, given any 2 points, there's exactly 1 set containing exactly those 2 points, which is the line containing them. Given any 3 elements, there is exactly 1 non-collinear elements, there's exactly 1 plane containing them. Well, that's certainly true, because given any 3 elements at all, there's exactly 1 plane, because the planes are all sets of 3 elements. If 2 points lie on a line and a plane, then that line is contained in that plane. So let's see how that works. So if we look at I3, so notice that we have that A and C lie in the line, AC. So that's the line AC. But AC also lie in the plane ACD. And we have that the line AC is contained in the line ACD. So I3 checks out for this specific example. Well, for this specific pair, AC. Now, of course, if we wanted to properly confirm I3, we would have to go through and check that this holds for all possible pairs of points and lines that they're contained in and planes that they're contained in, which is, of course, quite tedious. But we can check it pretty. We can check a couple of examples and see that everything is symmetric here. Everything works the same way. So this is the simplest geometry that we can work with. On the other hand, one of our most complex geometries that we can work with is Euclidean geometry. So Euclidean geometry is a geometry where our set of points, our space, that's what the capital S stands for, is the set of all points x, y, and z, where x, y, and z are real numbers. So this is just three-dimensional space, x-axis, y-axis, z-axis. So that'd be our space. Our lines are, well, it's the set of all. I'm going to be a little bit, I'm going to cheat a little bit here. I'm just going to call it the set of all lines in R3, i.e. three-dimensional Cartesian space. And P is the set of all planes in R3. And so here I'm using linear algebra. These things can be defined using linear algebra. So a plane is a set of points which satisfy a linear equation, and lines are sets of points that satisfy a pair of linear equations at the same time. So this is Euclidean geometry in three-dimensional space is very complex. Our first example had only 4 points in it. Euclidean geometry has infinitely many. Our first example had only 6 lines and 4 planes. And of course, Euclidean geometry has infinitely many lines and infinitely many planes. So we've got sort of 2 extremes here. Now, we are going to be eventually putting some more axioms on our geometry, and so we're going to start considering geometries that look more like Euclidean geometry than the simple 4-point geometry that we had before, but it's good to see what the simplest examples look like here. So let's look at one more example. Let's say, does the following satisfy I1 through I5? In other words, is it a geometry? So we can look at the set of points A, B, C, D, and we can look at the lines. One of our lines is going to be A, B, C, A, D, B, D, C, D. So there are 4 lines in this example. And the planes, we're going to have A, B, D, A, C, D, and B, C, D. So let's check the axioms. So I1, given any 2 points, there's exactly 1 line containing them. This is actually, this is true. This holds. Axiom I1 holds here. If I take 2 points, well, if one of them is D, then my line will be one of the 2, or one of the 3 2-element lines. And if both of my points come from the set A, B, and C, then the line containing them is the set ABC. What about axiom I2? I2 says that given any 3 non-collinear points, there is exactly 1 plane containing them. Well, this also holds, because if I want 3 non-collinear points, I can't choose A, B, and C. A, B, and C are collinear. They all belong to the same line. That is this one. So if I choose 3 points, one of those points has to be D if I want them to be non-collinear. And if I consider sets of 3 points that contain D, well, there are only 3 options. There's ABD, which does have a plane, ACD, which has a plane, and BCD, which has a plane. So I2 holds. So what about I3? Let's come back to that one. Let's look at I4. I4 says that if we intersect any 2 planes, then we get a line. Now let's check that out precisely. Let me give names to these planes. Let me call it P1, P2, and P3 for plane 1, plane 2, and plane 3. So P1 intersect P2 is the set AD, which is in fact a line. P1 intersect P3 is the set BD, which is a line. P2 intersect P3 is the set CD, which again is a line. So I4 holds. Now what about I5? Remember, there are 4 parts to I5. First, we need to know every line contains at least 2 points. That's clearly true. Then we need every plane contains at least 3 non-collinear points. Well, that's true. Every plane contains exactly 3 points, and they're all non-collinear. We need to know that there exist 3 non-collinear points. Well, they do. A, B, and D would be an example of it. And there exist at least 4 non-coplanar points, and that also holds. A, B, C, D, the collection of all 4 points in the space, are non-coplanar, and therefore I5 holds. However, I3 is going to fail to hold. So let's see why that is. I3 says that if 2 points are in a plane, then the line containing them has to lie in that plane also. So note that, for instance, A is in P1 and B is in P1. However, AB, the line containing AB, is the set A, B, C. That's the line containing A and B, which is not a subset of P1. And so that means that I3 fails. I3 would say that if A and B lie in P1, then the line containing A and B has to lie in P1 also, has to be a subset of P1. So I3 fails. This is not a geometry. Now, this shows that I3 is not a geometry. It also proves something else, though. It proves that we can't get rid of axiom I3. Something that mathematicians are concerned with a lot when we look at axiomatic systems like the one we're considering for geometry is, are they all necessary? Do we need all of these, or can one of them be proved based on the rest? So we might have asked, before we saw this example, we might have asked, do we really need I3? Maybe if we just assume I1, I2, I4, and I5, then we could prove I3 as a theorem. And what this example shows is that you can't. That if I1 and I2 and I4 and I5 hold, then I3 can still fail. So you can't prove I3 based on the other 4. Our first example we did proves that I5 can fail, even when the first 4 hold. That was our whole motivation for coming up with axiom I5 in the first place. And in fact, one can come up with examples, and I encourage you to do this. This is a good exercise. One can come up with examples of geometries that satisfy any 4 of these axioms and fails the 5th one. So we've got examples here where I3 fails and I5 fails. You can try and come up with ones where I4 fails, but the rest of them hold, I2 fails, but the rest of them hold, and I1 fails, but the rest of them hold. So these axioms are what we call independent of one another. Any one of them can fail even when the rest of them hold, which means that they really are all necessary. We can't just get rid of one of them and prove it as a theorem. However, there are lots of things we can prove as theorems based on I1 through I5. They're going to be very important results for us, so I want to go through a couple of them and look through the proofs. This is going to be a proofs-based course, which means that we're going to be looking at proofs in the notes and in the lectures, and you will be doing proofs as part of your homework. So I want to go through a few of them so that we can see some examples of how that works. So, the first thing I want to look at is Theorem 5. This one we're going to use a bunch. We're going to use these all the time. The intersection of two lines is empty or a point. So if I've got two lines, then they either don't intersect at all, or they intersect in a single point. In particular, they can't intersect in two or more points. So a lot of times when figuring out how we're going to prove something, it's a good idea to sketch out an example of what things are doing. So we're considering two lines here, and we're considering how they might intersect. And if we just draw two lines, then we can see, yeah, they're going to intersect once, assuming they intersect at all. And in particular, this means that we're not allowing ourselves to have a situation like the following, where we've got two lines that intersect in two separate points. We're not going to allow this to happen. Now, a lot of times, what we do to prove things like this, where we're trying to show that an intersection can only be one of a couple of things or has to satisfy a certain condition, a lot of times is we're going to use proof by contradiction, which means we're going to assume the opposite of what we want to prove and show that that can't possibly be the case because it leads to something that we know is false. So let's do that here. So let's suppose that we're in the second case right here. And in order to make the proof easier, we're going to want to introduce some notation. Remember, when you introduce notation, to always make it very, very clear what you are talking about and define your notation. So let's let L1 and L2 be two lines and assume that L1 intersect L2 contains 2 points for contradiction. Sometimes it's good to let the reader know when you assume something for contradiction that that's what you're doing, so that they don't wonder, wait, why is that happening? Why are we doing this? If you let the reader know what's going on, that's often helpful. So let's let L1 and L2 be two lines and assume that L1 intersect L2 contains 2 points for contradiction. Call those points P and Q. Now, by axiom I1, we have that there is only one line containing P and Q, because that's what axiom I1 says, that given any 2 points, there is exactly one line containing them. This is a contradiction. And it's a contradiction because we have that L1 contains P and Q, and L2 contains P and Q, and our assumption at the beginning was that L1 and L2 were 2 lines. That is, 2 different lines. And so this is a contradiction. Therefore, that means that our original assumption that L1 and L2 contains 2 points is incorrect. Therefore, L1 intersect L2 does not contain 2 points. Therefore, it contains either 1 point or 0 points, which is what the theorem was saying in the first place. So this is one way that we can use axiom I1 to prove a theorem that we're going to use very often, pretty much every day. We're going to use the fact that the intersection of 2 lines is either empty or a point, that 2 lines can't intersect in 2 different points. We've got a couple more theorems, the proofs of which you can find in the notes. But I just want to point out here because we're going to use them over and over. So theorem 6 says that if L is a line and E is a plane, then L intersect E is either empty or a point. So the sketch, not a proof, but a sketch of what's going on is the following. We've got a plane, and we've got some line that's coming in here and intersecting it. I apologize. I forgot one of our hypotheses here. If L is a line, E is a plane. We need in here, and L is not contained in E. So we need the line L to not be actually contained in the plane. Then the intersection is either empty or a point. So in particular, this is saying that we can't have the following. We can't have a line intersecting a plane in 2 different points. But we've actually seen this picture before. We saw this when we were talking about how axiom I3 works and why we have it. So the proof for this will use axiom I3. And so sketching out what's going on can help us to see what's going on. So theorem 6 is saying that this picture isn't possible, but that's the same thing that axiom I3 was saying, so axiom I3 is what we use to prove this theorem. All right. Theorem 7 says that given a line L and a point P, which is not in L, there is a unique plane E containing L and P. And theorem 8 says that if L1 and L2 are lines that intersect, their union is contained in exactly one plane. So these theorems and these axioms we're going to use over and over and over again. They're the basis of our geometry. And we're going to use them a lot, and eventually we'll probably even start using them without explicitly saying what theorem we're using because we've used them so much. I want to point out here something, though, that's very important. When you're proving things in geometry, using a picture is very helpful to organize your thoughts, organize your notation, things like this. However, it's never a proof. Your proofs should always be written so that they can be read without a picture and still be correct. Now, a picture is often helpful, as I say, for organizing things, clarifying things, keeping track of things, but a picture is never a proof. A proof has to follow from axioms and theorems that we already know to get from one stage to the next to the next. So, always keep that in mind.